pressing global challenges, extreme heat in urban environments, by integrating satellite data, ground-based sensor, health records, and socio-economic indicators. Rahul applies machine learning and geospatial analysis to study urban microclimates and their impact on human health. Importantly, his research goes beyond theory. He actively collaborates with local governments and urban communities to design equitable, data-driven strategies that help cities adapt to climate extremes, ensuring that the most vulnerable population are protected. Rahul has also contributed to innovative solutions such as wearable solar radiation shields for accurate heat exposure measurement and studies on how urban sensor networks can support climate resilience. His work aligns closely with several United Nations Sustainable Development Goals, particularly SDG 3, Good Health and Well-being, SDG 11, Sustainable Cities and Communities, SDG 13, Climate Action, and SDG 10, Reduced Inequalities. Today, he will share his expertise on how AI and geospatial tools can be leveraged to strengthen urban resilience against extreme heat, making our cities healthier, safer, and more sustainable. Please join me in extending a warm welcome to Mr. Rahul Devaji.
Hello, everyone. Thank you, Anupama, for the kind introduction. So yeah, let me share my screen and let's get started. Go. Okay. Okay, is my screen visible?
Yes.
Okay. Cool. So yes, my name is Rahul Devaji, and I'm presenting about how we can take global goals from sustainability development goals that the United Nations framework has given to provide local action through urban sensing to build climate resilience. About me, so I'm a PhD student and I am researching about it's all about building climate resilience, specifically focusing on extreme heat. I use machine learning, geospatial analysis to model the built environment by integrating satellite data, urban sensor networks, and health records to enhance the livability in cities, which particularly face extreme heat concerns. So Um, this is like the overview of everything that I'll be covering today, starting with the urgent pressing issue of climate change, which is worsening. And I'll talk about how it is a complex and global challenge. Like there's a lot of moving parts, which makes climate actions particularly difficult. Um, and I will be focusing particularly on extreme heat, which is the deadliest climate hazard that we are currently experiencing. I have split this talk into three parts: the why, the what, and the how. This is a visual of that where we'll be starting with the why by exploring the severe and unequal health and economic impacts of extreme heat to understand why immediate action is crucial and critical. Then we'll go on to the what, which is what tools are necessary to um, quantify the threat that we are facing. Like we will examine multi-layered big data technologies from satellites to personal sensors that are essential for accurately measuring this threat. Then finally, we will end with the how of this challenge, which is how do we collaboratively work together to turn this data that we collect into equitable real world impact and addressing the goals of the SDG 13. So please feel free to stop me anytime in the middle if you have any questions or queries. Also put it in the chat. I'll keep checking the chat messages. If you have any questions, please feel free to ask me them then and there. So yeah, before we get started with the talk, I am glad that I'm glad and I would like to thank Dr. Deepak for their deep dive presentation about the background and targets of various goals. And you all know that there are 17 goals, which are all basically a call to action. Like they are there to help us address the world's most pressing challenges. So today I'll be focusing on SDG 13, which is climate action, um, because it calls for urgent action to combat climate change and its impacts. Specifically, I want to talk about SDG target number 13.1, which calls for actions to strengthen resilience and adaptive capacity to climate related hazards and natural disasters in all countries, and then specifically targeting extreme heat as is one of the most critical of those hazards. So let's begin with the why of climate action, like understanding the urgency. This section will be split into three parts where we'll first go through the human cost of extreme heat and then understand what are the urban amplifiers of extreme heat, like how are cities being threatened more than surrounding areas. And then we'll look at how this situation will only get worse in the future. Okay, so let's start with the human cost. So this is an art a statistic from India, which is just from like what 2 weeks ago, that India had recorded over 7,000 suspected heat stroke cases and 14 deaths. The fact that someone had to file a Right to Information Act to get the statistic out itself tells you that uh, the state of the problem is not well understood by the public. Extreme heat is like the deadliest climate hazard, which is responsible for over 500,000 deaths globally per year. And Asia accounts for half of those deaths. And the latest national risk assessment shows that 57% of India's districts, which is home to over three quarters of our 1.5 billion people population, faces high to extreme, I mean, very high heat risk in India. So, cities are warming twice as fast as rural areas. And since a lot of people from the rural areas migrate to the cities, more people are being exposed to these high temperatures. And these populations, the vulnerable people, bear the brunt of this problem. Um, so, why do cities, why are cities more impacted by extreme heat? Right? So extreme heat impacts are magnified in urban areas due to the urban heat island effect. This is where city temperatures can be much higher than the surrounding rural areas, right? I love this visualization where they show that, okay, so the cities are hotter during the day and the night. I mean, it is sort of intuitive to uh, understand why this happens, because cities have a lot of paved surfaces. So during the day, the roads they get hotter, and since the surface gets hotter, it heats up the air around it. And since there is dense urbanization, lots of buildings around this in cities, the heat gets trapped in the city itself. So during the day, all of the cities get hotter and hotter. They will trap the heat, and during the night it gives out the heat. So this is how the cities are becoming hotter during the day and night. But if you look at the outside the rural suburban areas, you notice that they are much cooler because there is convective effects due to the airflow, wind and everything. So Surface temperatures have an indirect but significant impact on the air temperatures. For example, like if you take parks and vegetated areas, which are typically the surface itself is ground, right? So it is a cooler surface. So it contributes to cooling the air above it also. Uh, Especially you can notice this dip over here in the ponds. Like water has a very high heat capacity. So during the day, it what do you say? It absorbs all of the heat. Like the water heats up, and during the night, like that heat is just released out. So ponds and water surfaces, they normalize this heat effect, urban heat island effect, in places. So due to urbanization, like we are encroaching upon all of these ponds and trees, which provide us natural cooling, which is then, exacerbating this issue. So before I move on to the next slide, I'll just pause here for a second. Who do you think is the most impacted or affected by extreme heat in cities? So in our country, the informal sector employs about 82% of the workforce. And all of these people travel a lot every day and they are exposed to heat on a daily basis. They cannot, since it's an informal sector, they cannot take leaves. So they work in life-threatening conditions currently, and this is only going to get worse in the future. So, due to climate change and intense heat waves, the impacts are both on the lives of people working in the informal sector and in the loss of labor hours that results in them being not able to function to their fullest potential. So, between 2001 and 2020, India has lost an estimated 259 billion labor hours per year. So, I mean, I can't even imagine that number. It is due to extreme heat and humidity, and the loss is not just in the time absent from work, it includes slowed pace, taking breaks, um, and periods of periods when conditions are too extreme for continuous work. So all of these reduce the productive work time. So it's not just um, health wise, even economy wise, we are losing out due to not managing extreme heat. Next is I pulled out this other visualization from a report published recently. This was specific to India, where they show that the number of very hot days and very warm nights are increasing uh, each year. So higher nighttime temperatures, especially during extreme heat events, would mean that you do not have enough recovery time from all of the heat stress that you experience during the day. So, if it is hotter during the night, your sleep is also disturbed and you're put through more stress, physiological stress. All of these lead to a cumulative heat stress, which then increases your risk of mortality. Now, you might imagine that, okay, I'll just buy an AC and then run it all day. But air conditioning itself releases a lot of excess heat into local environments, which in turn increases the nighttime temperature in cities, right? So all of this, it's just it's compounding one on top of the other, and especially affects the vulnerable people like the elders and people with comorbidities. Oh, that's a hard word. And the unhoused, right? So these people do not have the adaptive capacity to adapt to extreme heat. So I read a research paper recently which said that if you have, if you're turning on the AC, you should also turn on the fan so that you minimize the usage of AC. Like there are so many things that we still don't understand the impact of. There was another research paper which said that if you're running just a fan and it's extremely hot and humid, the the fan is heating up the room more than it is cooling you. So it's it's a complex issue which has like a lot of moving parts, and each each aspect of extreme heat needs to be studied carefully. So summing up the urgent need, like we understand that the impact of extreme heat is alarming and that it is a complex problem which doesn't have a simple solution. You can't just have like a checklist of things to do when there is a heat wave and that you'd be safe, right? You need that we also understood that more people are susceptible to heat, and we sort of got an idea of who is most impacted by it, by heat. Now, SDG 13 gives us a mandate for action. So the next logical question is, what can we do? How do we quantify this UHI, urban heat island effect, or the heat risk? How do we find out who is most impacted by it? And how does what does this data and environmental sensing actually look like, right? So this brings us to the what section, where we will explore the specific tools used to measure extreme heat risk. So since heat is a complex problem, we need to look at it through different angles and at different scales. So we will start with the big picture and look at citywide patterns of surface heat from space. Then we will try to understand how official monitoring works on the at the ground level, and we'll understand its limitations. I will then propose a different style of monitoring using sensor networks to address some of these limitations. And then finally end with monitoring at the human level to understand the individual's true risk to extreme heat using variables. Okay, so before we get into the tools and monitoring, let's do a quick review of extreme heat to understand the need for monitoring in a better way, right? So, what is a heat wave? I mean, heat wave is not just a hot day, it is an extended period of extreme heat defined by local climatological conditions. And this extreme weather uh, event should last for at least 2 consecutive days, right? So here the key is local climatological conditions. I'll get back to that in a bit. So India declares a heat wave if, so this is one of two methodologies India uses. One, this methodology, it has used until like 2022, I believe, where it checks if any of the weather stations has its maximum temperature reach at least 40 degrees Celsius. And it has set two different thresholds for the plains and the hilly regions. So 40 degrees in the plains and 30 degrees in the hilly regions. If the temperature at a weather station crosses that threshold, then they look at what is the departure from normal. So how hot it is from what it usually is at. Let's say on May 15th, it is like 41 degrees. They'll look at all of the other May 15s in the past and see how much of a change this is. Um, Next, so different countries use like different conditions to declare a heat wave. Like in the USA, they use a metric called apparent temperature, which is also called heat index or the feels like temperature that you see on your phones. So the heat index is a metric which combines temperature and humidity. So they check if any 2 day period has daily minimum apparent temperature which exceeds the 85th percentile uh, minimum temperature record for that particular city for the months July and August. So they'll basically take the historical data from 1981 to 2010, and they'll take all of the weather data from August and July and August months for these 30 years. and then they'll calculate the daily minimum and maximum apparent temperature, and then they'll, order them and then take the 85th percentile value, and that becomes the threshold for that particular city. So coming back to the local climatological data, which is setting local thresholds requires long-term quality control temperature data, right? So if we have to set a threshold for Bangalore, we need long-term data for what the temperature is like in and around Bangalore from like at least the 1980s to 2010. So that will become your baseline. And using that baseline, you'll compare what the city level temperatures are. So, um, and this long-term data will help us like understand the impact of climate change, right? Where this you're basically comparing the global warming signal to the urbanization signal, and then you'll subtract them to understand what is the impact of urbanization. So so that you can clearly say that okay, cities are getting X degrees warmer than they actually should be, and you will see how like that is a challenge because weather stations, it depends on the places where weather stations are and how the data is coming from the weather stations. I'll get to that in 2 slides. So let's first look at satellite data. So satellite data gives us long-term, um, I think this first data, which satellite, which is called Landsat, it went out in 1972. So we have satellite imagery from 1972 to the current date from various different satellites now. So the problem with satellite is that it measures the temperature of the land. So land surface, meaning roads and rooftops. So it, I mean, the data is comprehensive, but it has its limitations that okay, it is just the surface temperature and not the air temperature, which is what we experience, right? So that this is good for viewing broad patterns of the urban heat island effect. So you'll know that, okay, this northeast area of Bangalore is hotter than, south, like Jayanagar side or something like that. Uh, and there are different kinds of satellites, which each have different spatial and temporal frequency, meaning um, like the MODIS satellite, it revisits a particular area on Earth every single day and night. So you have daily data, but Landsat, which has a higher resolution, which is that each pixel is 30 meters in size, and MODIS is like 1 kilometer in size. So there is always a trade-off between spatial and temporal frequency, I mean resolution. So satellite data is good for the big picture, but it has its limitations. Um, Next slide. Okay, so this is, I made this visualization about showing the summer mean land surface temperatures through the years. This is all the historical data we have from the satellites for Bengaluru. Um, where each image has pixels at 30-meter resolution, and I've averaged the surface temperature for the months of April through June. So since Landsat revisits every pixel or area every 16 days, we have like 2 images per month. For the summer, which is 3 months, you have 6 images. So that's 6 images per year, averaged across like 30, 40 years of its history. So in this visual, I mean, you can see that, okay, there is an increase and decrease in, surface temperatures, which is due to like the global patterns like El Nino, La Nina, right? So like Earth goes through these phases of increasing and decreasing. The thing that stood out to me the most in this visual is the fact that the lakes are vanishing slowly. Like in 1990s, you see this big lake, and you'll slowly start to see it disappear. So 2005, 2006, urbanization has, it's taking over. We've lost parts of it. Here it's starting to close up. I should have labeled this so that I could have told you exactly which lake this is. Must be Alsur Lake. I'm not sure. So yeah, so we already saw how lakes have a high heat capacity that they can normalize the temperatures in the surroundings. And now through the satellite imagery, we are seeing that we are losing lakes and how the surface is getting warmer as a result of it. So satellites are really good at doing this broad level analysis and creating some cool imageries. So now, okay, so we understood like the challenges with satellite data. Let's understand how all of our weather agencies, all of the meteorological departments monitor the surface conditions and weather for us and give us predictions. So every notification that you get on your phone which says, okay, tomorrow it's going to be sunny with a 30% chance of shower, it comes from this huge data set of sensors and weather stations across the world. So this is called the Integrated Surface Network, surface data set, which has a global collection of high quality long-term weather station records. Um, like each weather agency across the world has its own, like in India, IMD manages the data from these sensors, and I think NOAA just aggregates it for the entire world. Um, So these weather stations, they provide standardized and accurate air temperature, humidity, wind, precipitation, like visibility, a lot of weather data, and they usually have a long historical record. Like I'll show you for Bangalore, it goes all the way up, all the way to 1942. So you have daily, hourly weather data going all the way back to 1942 to the present date. Now, the location of these weather stations matters a lot when you're trying to perform these UHI analysis or any urbanization analysis. And we have established from the previous slides that local weather thresholds require accurate and long-term data, right? So the location of these traditional weather stations presents a fundamental dilemma, like creating, there are these two problems from these two cities that I'll show, but there are other problems too. But these are like the main ones. And this will tell you why. Oh, did somebody have a question? Sorry, I can't hear. Okay, I think someone needs to be muted. Okay. So, these are, yeah, okay, yeah. So the two problems with weather stations. Bloomington is where I live, and Bengaluru is where I used to live. Let's start with Bloomington. So you can see this is the center of the city, and the weather station is somewhere outside. It's not that far from the city, but since it is outside, it is in an open field, right? So I am calling this the rural bias, where the weather station is outside the urban core. So station measures cooler surrounding environment temperature, and it won't know exactly how hot the city is, right? So the residents could be facing heat stress sooner than the official heat wave declaration. So what I mean by that is when you get an alert on your phone, which says, okay, it's going to rain in 2 hours, or that in the next 3 days it's going to be this hot during this time, and you're not supposed to go out. So all of those data and those thresholds are coming from this weather station outside the city. So since it is outside the city, the it this sensor, let's say the threshold is 40 degrees Celsius. For this sensor to reach 40 degrees Celsius, it's going to take longer than, let's say, hypothetically, you keep a sensor in the city. It is due to the urban heat island effect and due to the heating of the surrounding areas, it will reach 40 degrees Celsius sooner, maybe the day before itself, right? So these sensors outside the city will underestimate a city's true heat. The next problem is of Bengaluru. I haven't put labels here, so I'm going to go back to this slide where I have the labels. So the earliest sensor which was there for Bangalore is at the HAL airport. So that was put in 1942. So I'm not sure how big the city was back like 120 years ago. So I'm guessing maybe then the sensor might have been outside the city, but since then HAL now is like in the heart of the city. So first they kept the HAL sensor that had data from 1942 to 1976 or something. And then in the meantime, they set up another sensor, which is directly in the middle of the city. So this sensor has now climatological data from the 1973 to present date. They also set up another sensor at the airport, which is way outside the city, but it's only been set up in 2008. But 2008 doesn't have good enough data. I think it only has for like 1 or 2 months. From 2009, it has good data. So this is what we can call an urban contamination, where the urban growth skews the historical temperature baseline, right? Now, if I'm calculating the threshold using the HAL sensor, the threshold will obviously drift upward from the baseline because the urbanization has, normalized the temperature that this sensor is, observing. So it will, over time, it will mask the urbanization signal that you're trying to measure, right? Now you do not have a good baseline itself. So the baselines are calculated from the years 1981 to 2010. So from 1981 to 2010, all of the three sensors that you have are all within the city itself. So you don't have a good baseline outside the city to to give you a comparison. So the station is, so whether the station is too far outside or it has been absorbed by the city, it is meant to monitor. The conclusion is the same, where we cannot rely on these isolated stations for effective urban heat action or risk measurement. So this calls for a different approach itself to measurement. I'm going to pause here for a second if anybody has any questions. I don't see anything in the chat. Okay, I will continue. So the solution, so when you, yeah, okay, so the solution is to understand the impact of urbanization and the impact of heat for people living in cities is to deploy sensor networks inside the city, right? When you combine the long-term data from the weather station with the sensors that you have inside the city, you can sort of understand the impacts of urbanization in a deeper area specific or a quote unquote hyper local manner. So this way you will know which parts of the city are warmer and by how much. So this figure on the left shows the sensor network that we have deployed across the city. So these sensors measure near surface air temperature, relative humidity, and dew point temperature, which are like the key metrics to measure heat index. And heat index is normally used to understand the health impacts on humans. So there are some more images from our sensor network where it was built and expanded thanks to the support of the National Science Foundation, the university, and the city of Bloomington and community partners. So we took help from all of these people to build and expand our sensor network. So each sensor measures data at 5-minute interval. So this this figure shows you what the sensor looks like. This one on top is the data logger, which stores the data which the sensor observes. So the sensor itself is as thin as my index finger, but it is housed in this huge white color solar radiation shield so that the sensor does not overheat to direct heat exposure, right? That's how it will measure like the true air temperature values. So we have deployed the sensors on top of light poles, electricity poles, and parking signs and everything. And half the sensors are Bluetooth enabled, and then half are live. So yes. Before I go to the next slide, I have a small question. If you were to design a citywide sensor network, where would you place the first few sensors, or how would you choose locations for your sensors? Just look at the chat. You can even unmute yourself if you have any thoughts. Okay. So the goal is to understand how different parts of the city are hotter or cooler, right? So for that, we would need a framework to sort of classify the city into different zones. So that is what is called the local climate zones framework, where it is a built environment modeling framework. This enables us to classify cities into 17 different classes, as seen on the left over here, where you have stuff like compact high rise, which are like high rise buildings which are densely packed, you see in these big cities. And then you also have bare soil or sand, which is like open grounds and all. Bare rock or paved is all of the paved surfaces, parking lots. Dense trees are like forests, like Carbon Park. Scattered trees will be some small parks. Industry is like factories and stuff. So, like this, you have a universal typology to classify any city in the world. So, this framework was born out of the limitations of the insufficiency of the tags urban and rural. Like what is urban and what is rural in one country may not be termed as the same in different countries, right? The tags don't have any single objective meaning, and there's no climatological reference or relevance to urban or rural. So it is impossible to comment on the physical structure of the city or the surface properties of the city uh, by just calling it urban or rural. Like we are missing out on a lot of detail, like what parts of this urban area are hotter and what makes them hotter. So to answer those questions, this framework was born, and we used this framework to first classify the city of Bloomington into various zones. And note that every city will not have all 17 of those zones. Like Bloomington is a smaller, it's just 23 square miles. So it's smaller than one phase of Jayanagar or one block of Jayanagar. Wait, there's something in the chat. Okay, there's some questions. What percentage of efficiency of sensor data can be considered for collected data analyzation? Sensors near industrial area or inside the city? Uh, okay, so percentage of efficiency of sensor data, meaning, are you talking about like quality control? Because, wait, let me, it's going too far. Okay, cool. So so we collect all of the data. So the what do you call it? The infrastructure design now is, like I said, there are two types of sensors. One is Bluetooth, one is wireless. So the Bluetooth sensors, like somebody has to go to the sensor, they have to push a button, and then that data gets downloaded to their phone, and then from there the data goes to the cloud platform. From cloud platform it goes to our server. From the server it goes to the database. So once it reaches the database, we have implemented uh, like some QA QC measures, like we're looking at uh, if let's say you have three measurements within 5 minutes, if there's like a huge jump, or we're checking it based on standard deviations. So if the observation is within one or two standard deviations of the observations that have come before and after it, then it is a valid observation. Otherwise, we are flagging it for further inspection. And then we also, as we are monitoring the sensor network, if the sensor has been moved or displaced, or like, yeah, we have flags in the database to say that, okay, this data point is valid or not, and what is the issue with it. And the sensors are inside the city. So there is, like I said, this is a small area. I mean, the city is pretty small. It's 23 square miles. So there's no industry around it. There's a lot of greenery, and just the city center has a lot of buildings. So yeah, it's not next to a city. Anuradha, does that answer your question? Okay. Um, Great. Yeah. So LCZ classification. Oh my God, I keep pressing the wrong button. Okay. So LCZ classification was done using Google Earth Engine, which is a cloud platform used to perform analysis with satellite data. We used the same Landsat satellite data that I showed you, which had the long term, that video. And we used a random forest classifier. So we created training areas for the entire city. So we just drew boxes, and then manually said that, okay, this is LCZ1, this is LCZ2, this is LCZ water, stuff like that. We created this training data set, and then we put it into the random forest classifier, and then we got this map, which is at 30-meter resolution, meaning each pixel that you see over here is 30 meters by 30 meters, like length and width. So yeah, so we classified it, and then we decided to put a sensor in each one of the classified local climate zones. And we also partnered with the city to tell us, okay, we wanted to put few of them next to schools, few of them next to like low income neighborhoods, stuff like that, to ensure that we are covering all range of microclimates and a range of people living in the cities, right? Uh, so all of the yellow are spread across the city. The blue ones are in and around the campus of Indiana University. And this pink, it's just one dot, but in that area there are 13 sensors. So that is a very high density mesh network. So this allowed us to perform analysis and tell that people living in local climate zone 5, which is open mid-rise. What is open mid-rise? Is an open arrangement of 3 to 9 story sized buildings, which has like some scattered trees around it. So that area has like, in those will be this darker, slightly darker shade of orange in this image. Uh, so those areas experience twice as many heat wave days compared to people living in other zones. So we have seen that satellites can give us long-term broad trends. And we also looked at how weather stations provide us with daily weather data. And finally, we looked at how deploying sensor networks to measure neighborhood level heat stress can be measured. Now, there is a difference between what a person experiences in the moment and what a person experiences throughout the day. Like, let's say a person is going from a bus stop to their department or their office or wherever. So these fixed sensors in the environment, they cannot track that person's journey, right? Um, so wearable sensors help us measure this journey of a person through the environment across a day or multiple days. So these sensors, they'll give you like the true experience of the humans. Um, so these sensors are called eye button sensors. They're sort of like a watch battery, but like much little bit thicker. And they're really, really expensive and very finicky to work with. Like each battery that you see over here is like $100, which is like 8,500 rupees. And it requires a special tool to extract the data. All in all, it's a pain to work with, but it enables us to, put the sensor on someone. Like the person won't know that they're wearing a sensor. Like this is my advisor wearing it as an ear ring, right? It becomes fashionable, and you are contributing to citizen science initiatives, right? Um, so if let me go back. So these were the sensors which we had embedded in the city, right? I told you about how it's the size of my index finger, but it requires a shield to sh- shield it from solar radiation, direct solar exposure, right? So similarly, we had to shield these watch battery sized sensors from the solar radiation. So we designed 3D printed earrings, which will act as those shields. And then we published a study on it, which basically said that okay, the bias in between the measurements of these tiny sensors and our standardized big sensors is only 1 degree Celsius or 1.87 degrees Fahrenheit. So this, lets us understand the risk of heat from different angles, right? Like you looked at, oh yeah, before I go to that, what do you think might have been the challenges that arised when we tried to, put sensors on people for data collection? Just, it's just a, just a fun question. Like I wore it too. I don't even have those holes in my ears, but still I hooked it to my ear. But so the main challenge is if a woman, yeah, it's radiation, yes. So when you put it on both your ears, it depends. So the ear which is exposed to direct heat, it still heats up more than the side of your body which is not exposed to direct heat, right? So I noticed it myself. So that means that half your body, like at different parts of the day, half your body experiences more heat than the other half. And if a woman is wearing, like, her hair will also provide some cooling effect on the senses. So it's a little hard. It's not as, like, you would have to account for a lot of variables if you are using this form of wearable uh, temperature monitoring. Next is, okay, so we are nearing the end of the presentation where we've journeyed from like the 30,000 foot view of satellites down to the individual level of wearable sensors, right? So now we have an incredibly detailed, multi-layered understanding of the heat problem, but the data sitting in my database has no impact, right? This brings us to the most critical part of our discussion, which is the how. How do we bring about climate action, right? How do we transform this rich data into meaningful real world action that builds resilience and protects people? Also, note that I'm calling it equitable action because it is the action taken to ensure that all individuals, communities, regardless of their circumstances, have access to the resources and opportunities which are necessary to benefit from the development or any initiative that we undertake. Like, that is the core tenets of sustainability development goals, which is equitable action for all. So, the problem of climate action is not the lack of data, but it's the challenge of implementation. So, going from raw numbers to meaningful action requires access to information, ability to interpret this information, and the willingness of people to engage with the data. So, this final section, I've divided it into four parts. One is we'll first look at how we are going to visualize this data, and then we'll how do we perform some root cause analysis to sort of explain, okay, why a part of the city is as hot as it is. Then we'll look at building indices to give a holistic representation of heat risk. And finally, we'll discuss the three-legged stool framework to sort of uh, give a framework for all of these collaborative actions that are needed and that I hope you would also undertake in the project that you would perform in the future. So, first step is making the data visible and accessible. So this is from our sensor network. We had originally started with making Tableau dashboards. Okay, we, visualized the data on Tableau, like in time series, and then we labeled it and everything. But the problem with this is, so I have labeled these as the green is Dunwood's, red is Miles Brand, and Wells is library. So unless you're in the city or if you're on campus, you won't know what these three locations are just by looking at the graph. Because of that, I have added this additional visualization next to it which says, okay, this is Miles Brand, it is an empty barren parking lot, and this is Dunwoods, which is an old growth forest in the middle of the campus. And they're like hardly I should say 300 meters or 400 meters away from each other, but there is 10 degrees Fahrenheit difference. So 118 degrees Fahrenheit is 118 F is 47 degrees, and 107 is 41. So that's like 5 degrees. Slide not changing. Okay. Sli- What can you see right now? You're seeing slide number 38, right? 118F. Oh, okay. That's weird. Let me share again. Okay. So there's a difference of at least 5 to 6 degrees Celsius. Can you see it now? I lost my Zoom chat. Bring chat again. Okay. So yeah. So is it proper now?
Yes, sir.
Okay. Cool. So there's like 5 to 6 degrees Celsius difference within like less than half a kilometer, right? So this spatial interpretation you would not have known if I had not, brought these additional images. If I had just given you this time series visualization, you would not have known, okay, why there is such a big difference, right? So standard dashboards will they're a good tool for what do you say, understanding what is happening and where, but they don't answer complex questions like which communities are most at risk or which area is consistently hotter or what makes a location hot. So for that, we created a spatial visualization where we overlaid the temperature data on satellite data to give, let me open this link. Can you see the browser now? No. Let me share this window. Okay, can you see the browser now?
Yes.
Okay. So yeah, so we created this spatial interactive visualization, which will sort of let you zoom into different locations. And then, okay, let me click on this sensor and then it's going to pull up all of the data that we have. Here, you can see that, okay, there is some missing data that I have for this particular sensor. And I have also overlaid like the temperature from the airport. So you can see at some points, right, let me go back to, yeah, there we go. Okay, so you can see, okay, so the one in blue is for my sensor, and I have also overlaid what is the temperature at the airport at that given time. So this gives you like uh, an understanding of, okay, this sensor is this hot at this particular time, right? And yeah, so this was the high density mesh network that I spoke of. It is in the garden that we have, where we have solar radiation, wind, and all of like different sensors over here. And they're all used to monitor different aspects of the city. And this was for the urban garden. Let me go back here and I'll have to stop sharing, start sharing again. Sorry about this. Okay. So let me briefly talk about another method of data collection, which is, I mean, it's both a data collection and citizen science initiative. This is that's from a company called Kappa, which send out sensors to different cities based on like to map out the city's heat footprint. This was one such campaign. Like they've conducted this campaign for over 160 cities across the world, and the only city that they have performed this campaign for in India is in Surat, and it's I think Gujarat is especially I interesting because Gujarat was hit by Ahmedabad was hit by a massive heat wave in 2010 2011 time that killed like 400, 500 people just in that one city. So that prompted the local government to take action. And in 2014, Ahmedabad was the first city in India to come up with a heat action plan where the heat action plan basically says that uh, it's basically split into like four different phases. One is pre-heat, pre-summer, and then during the summer, after the summer, and then analysis. So before the summer, what are you supposed to do to prepare for a heat wave? That's when you do all of the analysis. You'll take stock of where you have all of the resources around the city. How do you protect people? Where do most vulnerable people live? How do you reach out to them? How do you bring awareness to them? Then second is during the heat wave. Okay, how do you support the people in the moment? Like, can you go give outdoor workers water, people who are living on the streets? Can you provide them additional support? And after the heat wave, okay, then you take stock of what has happened. How can you do better? So Ahmedabad was the first city in India to do that. Since then, I think over 60 cities across India have come up with their own heat action plans. I'll show you the website where it's all stored. So this was a community driven effort for data collection. So as you can see here, this woman is putting a sensor on the car, and what they do is they drive around fixed routes. So all of these are different routes, right? Surat is, I mean, that's a massive city. We did this in Bloomington, which is a very tiny city, and it took a lot of effort. So the fact that they did it in a big city like this, it means that it's a tremendous achievement. So, um, so you drive around these predefined routes at different times of the day. So you start at first will be at 6 a.m. in the morning, and then another at in between 12 and 4 p.m. Sometime you'll take another hour time slot, and then you'll drive around again in the same route. And then again you'll do it night or evening, like 7, 8-ish time. So this lets you map out the entire city. So these on the left you see are all of the individual data points that were collected as the car moves through the environment. And right is the interpolated map. Sorry for switching it back and forth. Let me open this link. And I think I might have to. Oh, can you see the browser? Yeah.
Yes.
So, okay, okay. So thank you for confirming. Sorry. So yeah, so this was the Heat Watch campaign that was conducted in Surat, where, yeah, let me see, where was the background? Yeah, it was an all women led, what do you say, effort in conjunction with the Mahila Housing Trust. So it there were two outcomes of it. One was to develop high resolution spatial maps to understand the risk of heat across the city in Surat. And second is this is the main part, right? You are building awareness amongst the environment, I mean, amongst the people in the city. So that you are educating all of these people who will then educate all of the people that they know. So it is a compounding way of saving more lives, right? So this is a beautiful story map that they have created. You can see that they mapped out. Uh, so yeah, different. So in this one image, you have 55 degrees to 7 degrees difference. So this is how they first plan out the routes and then they drive around. Yeah, I think here you can see them going around in autos and driving across the city. So this will then give you a mean temperature, at different times of the day. This is the map, different routes. So they tell you, okay, which parts of the city are hotter, which parts of the city are cooler. Like I'm guessing this is a richer neighborhood because obviously rich people, richer neighborhoods obviously have a lot of trees. So that is like the divide that we observe in most cities across the world. So let me scroll down all of this. Mm, like I'll yeah, this part. S- Okay, this hasn't loaded yet. Okay, yeah. So they let you swipe through and compare. Okay, this is in the morning and this is in the evening. But when you look at morning and afternoon, you see how hot the afternoon area is. Of course, I think there will be an impact of humidity because it is the humidity which makes makes a city or a region very hot, right? So if I scroll through all of that, they also gave a historical heat waves by year. So ideally, I mean, what the trend you would see is the intensity and frequency of heat waves would only increase as you go through the years. And yeah, let me go back to the slides. Oh, wait, let me skip that. Okay. So I couldn't find this particular visualization on their report, but the idea is that you will know exactly how hot it is currently. And then using the climate models, you will project how hot these regions would get if the carbon emission remains the same in the future. So by 2100, I think the middle map is a medium prediction, and the last map is about high carbon emission prediction, right? So it says all of these regions, and this is in a tiny town which is surrounded by forests, and this place itself is going to get 100 degrees Fahrenheit hotter so that's like 15 degrees hotter in the next 50 years. So I can, and Surat, which is already at, I think, close to 90s or hundreds, it's going to cross to 110, 120. So the average temperatures would become close to 50 degrees Celsius. So now we understood like the different ways of collecting the data and visualizing it, but how do we uh, go from visualizations to public policy and planning, right? Which then also comes into the root cause analysis, where you have your temperature maps, right? Which kappa has created. They give you, like for Surat, they give you this very high resolution temperature maps, but what are you going to do with it? So first thing you could do is overlay it with the built environment data, where let's say we have a map which lays out where all of the streets are and where all of the trees are. So then you can have some idea of, let's say, this hot area has, a percentage of 70% buildings, 10% streets, and only 20% trees. So that'll give you a sense of what you can do in that particular area to uh, make that area more resilient. Next is, you could also layer population level data on it, right? The ultimate goal is to protect people. So you first start with your exposure data, and then you start with your susceptibility data, like what makes people susceptible to extreme heat, which is, uh, 1 second. Okay. Which is like the built environment around them, right? And then you add in the population data, which says how many people are living and where are they living. So then you will get an idea of, okay, there are like 1,500 people living in this one uh, zip code, and they are the most impacted by heat, which is because of that area being 30, like 80% built up area, right? Then you can also layer in the health data that you get from hospitals. Like this is, I'm glad that uh, the I'm sorry, I forgot their name yesterday. They came in and they gave their talk about healthcare data, right? You can take the healthcare data from all of these hospitals and then you layer it with where people are living, right? So that will help you understand what are people being diagnosed with in hospitals during extreme heat events, right? And you'll know whether, so the problem with extreme heat, I mean heat waves and health data is that it is very messy. So I'm working on a data set which has we had to buy the data from a company which aggregates the data from multiple hospitals, and you can buy the data from them if you say that if you prove from your university that that you're using it for research purposes, right? So the problem with that is we had like tens of millions of data point like rows in that data set, and when I aggregated all of the heat related illnesses across the past 10 years, there were less than 100 for the entire city of Bloomington across 10 years, right? Which means what? So when people go to the hospital due to extreme heat related illnesses, they are usually going with, or they are usually being diagnosed with something else. Like they might have heart problems or something, or they might be diagnosed with respiratory illnesses, or they might have issues with their gastrointestinal or renal problems, right? So all of those other diseases become markers for extreme heat related illnesses, but you won't see a lot of people being diagnosed with heat or heat stroke specifically. I mean, that might be the case in for me in Bloomington because extreme heat is not that big of a problem in this locality yet, but I'm sure it might be in India, right? Maybe the doctors are using the exact health codes to diagnose people. So the challenge is to have good diagnosis data and to have good address data for the patients who are going to the hospital and being diagnosed with, so that you can use them to, overlay on top of each other and then let you answer questions like, why is there such a big difference in life expectancy between regions within a single city? What are the like drivers behind this reduction in life expectancy? So this is for the city of Indianapolis, which is just, I think, 60, 70 kilometers above where I live. It's a big city itself. Let me go back to here. They gave a interactive graph. So here it shows that if you're living, this is at the top is one of the richer neighborhoods, right? So their life expectancy is around 80 years old. But when you come down to the city center, this is where all of the big buildings are, your life expectancy drops to 71. So there's a 10-year, what do you say, difference in life expectancy based on where you live. So in order to understand why this happens, you need to sort of, layer in multiple data sources and then understand all of them spatially. Then you can say, okay, people in this locality are living lesser because that locality is much hotter, or the air quality in that locality is much hotter for more number of days in a year compared to the other localities in the same city, right? And obviously income matters, so I'm sure poorer people live in the center of the city. Especially it's a phenomenon in the US where richer people live in the suburb. They call it the suburban lifestyle, where They have these huge houses outside the city, and then they travel to work into the city, and all of the cheaper um, housing situation is there inside the city in the downtown area. So the final the final goal is, as we said, like bringing justice to people by combining all of the data sets that we collect, right? So this helps us create a heat vulnerability index. What is an index? uh, a high temperature reading is a hazard, right? But the actual risk depends on who is exposed, specifically because not everyone is equally affected by heat. So, a heat vulnerability index combines demographic data like age, sex, age, all of, I said age twice. I mean, their, comorbidities, pre-existing health conditions, urban greenness, the perviousness or the imperviousness of the surface. So, the map you create using this methodology doesn't just show you where it is hot, but it also shows you where the heat will do the most harm, so that policymakers can precisely target interventions like building cooling centers or tree planting or other outreach activities. They'll know exactly where to start from. So this map shows you, wait, let me turn off. So this is for the city of Philadelphia in Pennsylvania state. So it shows you everything in this dark red are high heat vulnerable areas. That means people living in, oh, zoomed in too much. Okay, there we go. So people living in these areas are the most susceptible to extreme heat. So when a heat wave hits, this is where you need to concentrate first. This is where people need the most help. So they've also laid out where there are health centers. So all those plus marks are health centers, right? So there are health centers, but there's no, let's say, cooling center in these three blocks. That means, okay, that is a potential for intervention where they can build, let's say, open water taps or something like that for people to, cool off during an extreme heat event. So this level of detail can be achieved and is great for policy making because you'll know exactly where to target um, your efforts. Any questions so far? Okay, we're on to the final stretch of the presentation. Let me go back. Right. So now, true impact requires partnership and shared ownership, right? What does this mean? Each stakeholder, so right now we are considering researchers, like we are all researchers, everybody in this session. And then there are city agencies, which is the government. And then there are local communities, which may be NGOs, or it might just be citizens, right? Each stakeholder has their own unique set of challenges and goals that need to be negotiated. Okay. So calling back to the three questions that we had posed before in the start: what, why, and how. So we as researchers and people in academia, we do the what part, right? We, I mean, some part of why too, right? We do the what part in the sense that we build the tools, we build the technology to sort of understand the impact of extreme heat, in this case, in the cities. The community, which is the people, they give you the motivation for why, right? They know exactly what problems they are facing so that they can provide expertise from their own lived experiences for you to understand where to focus your efforts. The city and the government, the city council, the government, they just provide the means and the power for the how. Like they will give you grants, initiatives to drive research for public good. They also, they're also motivated by the push and the concern from the community partners, from the people regarding, the public issues. The issues faced by the public. So all three legs, so it's called a three-legged stool because you cannot sit if any one leg is broken, right? All three legs are vital. If one leg is weak, the effort is unbalanced, the chair is unbalanced, and you fall down. So let's start with like the motivations of us in academia. Like we provide the scientific rigor, we develop innovative solutions, we ensure that the data is accurate and credible, and like our primary incentive is to increase the knowledge, like the to advance the knowledge, to secure research funding, and publish impactful work in the end, right? And then also train the next generation of scientists. But the problems we have is that we are highly dependent on the research timeline or the academic timeline, which is that it takes a long time for us to get a grant or to get funding from some sources. And then by the time we go to the community and then implement a solution, like we'll collect all of the data from the community and then we'll go back. And then by the time we publish the result, like the academic timeline is years long. And that clashes with the urgent needs of the community and the political cycles, which are in like months. So, gaining that trust from the community that they shouldn't feel that, okay, you're just going to come, you're going to ask some data, you're just going to collect some data, and then you'll go away and then never talk to them again. So, our job is to build that trust with continuous engagement with the community, right? Which then brings us to the city and government agencies because they have the authority to translate all of the findings that we give into policy. So they can deploy resources, they can change regulations, they can integrate the resiliency planning into their long term urban planning goals, right? And their motivation is to serve the public, protect the health of the residents and safety of the residents, and enhance the city's economic vitality and livability in the long term. So they like the main challenge with the city is that they operate in limited budgets, and all of the departments within the government are often siloed. Like you don't know if you have to uh, like if you need something to get done, you will have to go through multiple hoops, you'll get redirected to different departments. So much time gets wasted in bureaucracy. It is such a hard thing to do. So we as researchers, we're like at the central between, we are like the mediators between the city and the community partners. We need to navigate the challenges of the city while maintaining the trust and relationship with the community, right? And also we need to give the city data that is easily understandable and directly actionable. It should not just be academically interesting. Like we might find a lot of things like the earrings that we developed, we got a lot of response from the academic community. Like a lot of people wanted to get use the same designs in their own research, but obviously it's not something that the city would want to investigate or develop on. Finally, the community is the most critical. Like residents, non-profits, advocacy groups, they all provide essential lived experience that validates or challenges the data. So we had our lab had conducted a workshop with the city council members, like the city's heat action task force. Like involved people from schools, people managing homeless shelters, people managing the emergency systems, fire, hospitals. So we got like 15 people in the same room to, like, getting them in the same room itself. That is the first challenge because you'll have to manage the schedules of everyone. Then once you get them in the room, you have to so what we did was we conducted tabletop exercises. Like, we give them scenarios saying, okay, now there is a um, okay, like the same 3 4 phases which I talked about in the heat action plan. We give them a scenario saying, okay, now there is a heat wave, how do you manage it, who contacts whom, how do you map out the interactions between different departments so that you can reduce the friction. So we in the academia can conduct such exercises with the city officials and community officials to understand, okay, who is facing challenges? How can you enable communication to reduce friction? It's like through this, what do you say? Through this workshop, we got to hear a very uh, heart touching story of, there's a person who works with the homeless shelter and like with the poor people. So she had one pregnant mother, and she had a small, like, 7-year-old kid also. They didn't have AC at home, so they had to rely on driving around the city in cars with the windows rolled down so that they could stay uh, cooler, because heat also uh, puts strain on the pregnant women. Like, there can be pregnancy complications. We have seen in the health data that uh, there are uh, increased number of I'm not sure if I don't know if this is statistically significant, but there are research which say that it impacts pregnancy also, right? So we as researchers won't know of the ground realities of the pain points that people are suffering unless we go out and talk to the stakeholders, right? If we had not sat with the the NGO workers or the people who manage these shelters, we would not have known all of these stories. Like, sometimes we got another story from a school where the students were made to work out in the hot sun. Like, the student athletes and stuff, they usually, it doesn't matter if it's hot or cold, they always work out. So the person managing the schools, he told that, okay, from now on, through this workshop, I got to know that I should take more care, right? It's a two-way street where you learn something, they also learn something, and all of this happens only when people come together and talk to each other and not stay in their silos. So finally, how do we support this effective collaboration? As researchers, we need to build capacity with the city. Like, obviously the city will have one person working on sustainability development. Like, how will one person manage all of these together? So we need to help them out, and also help out the community people, because, like, all of us share the same problems. And if you have the ownership of that problem, you will find different ways to fill in the gaps. And like how we did in the what do you say, sensor network planning, we just gave the authority to the cities and the community partners to help us decide where to keep the sensors and stuff, so that they will know exactly where the issues are, so that they'll help you use your data technologies in the right way. Finally, I just have one, interaction question is who do you think should take the lead in climate resilience planning? After this, we'll take a, short 5-10 minutes break and then we'll come back and go into the demo. Any thoughts? I'll go back, I'll stop sharing. Yep. Cool. Then can we, Meenakshi ma'am, can we break?
Yes, we can take a break of 10 minutes. At 8:15, we will join the session.
Cool.
Dear
Thank you.
participants will join the session at 8:15. Dear participants, can we start with the session?
Yes, ma'am.
Once again, welcome you all to the session. Now I request Rahul to take over the session.
Okay, welcome back, everyone. Let me share my screen again. Okay, so this was we discussed about the three-legged frame collaboration framework, three-legged stool, sorry. So this was a framework implemented in the city of Chicago, and it was called the Project Eclipse. You can Google it. And a brief introduction about city is it is very segregated. So you can see that everything in blue is all of the neighborhoods where black people live. And then there's clear segregation between Mexicans and Hispanic people. Asians are a small pocket here, and the rest of these are the outskirts of the city, like before. It's of white people. So how this so they wanted to the city officials partnered with the University of Illinois Chicago, I think, and they wanted to build a high density sensor network to understand health outcomes. So they were monitoring both air pollution and temperature and weather data. So they started with conducting workshops and seminars with the three different stakeholders that we have: the researchers from the academia, then the city council, and then the community, some people in the community. And they asked each of the people in the city and in the community, like, what are the issues that concern them the most. So for the city, it is obviously about like they want to empower groups, they want to change their policy. Even in the US, there are, there are rules they have to follow to ensure that emission levels in the city are controlled and all of that. So those are the motivations for the city. And then for the community, obviously, they wanted change in behavior. They wanted people to have they wanted to empower the people themselves with the knowledge to advocate for themselves. So if they know that, okay, they are living in a high vulnerability area, they can sort of vote in the right people, or advocate for themselves or voice their concerns in the right way. All of this will only happen if people are given the data, and the people are able to interpret and advocate for themselves through the data, right? So first they did this consensus analysis, concern of analysis, I mean, analysis of different concerns of different stakeholders, sorry. So they then um, set out to so this was the original uh, network of weather stations across the city. So obviously Chicago is a very big city, and there were only four monitoring stations in the city. Then these are all of the crowdsourced. It's like people keeping sensors in their backyards or in their garden, and then making their own data accessible to the public or to the government to act as additional data sources. So they said, okay, this is also not enough. So they set out to, design their own sensor network based on the consensus and, uh, you know, after talking to all of the city community people and the city people, they designed a very high density sensor network, which put sensors on bus stops across the city to manage, to monitor the city's weather and heat exposure and air pollution data. So this was the outcome. So On the right, you can see the mobile app that they had created. Like this is a bus stop, and on the bus stop, that is their device that they had deployed. It contains an air quality monitor along with other bunch of different sensors. So they created a mobile app which gave instant access to data. They also set up pop-up shops across the city, which gave the same data, but in the environment itself. So this would probably be near another sensor so that through this pop-up shop, they could explain to the people exactly what the sensor is collecting. Like some people will have concerns, right, about what is the government putting in the environment to track them. So these pop-up shops were put up in the city to raise awareness amongst the people. So, and this was also then picked up by the news channels, and then all of the promotion happened. But so this was deployed in 2020, I think it was 2021, 2020 to 2021 sometime. Um, the data is still accessible, but there is no news about what the city is doing with this data, right? So there's still some sort of opaqueness or challenges which you can imagine, like the city should have the funds to support this over the long term. Like sensors require constant maintenance. Someone might steal the sensor, someone might throw rocks at it, break it. All of this requires continued supply of funding. Also, researchers, once they publish a paper, they might become less interested, and they also will not have fundings to keep supporting the project. So those two people, the first two to disengage will be the city and the researchers. So now the community is, they're left with the stale data, because even the app doesn't work, it doesn't exist. So it's just there's an API endpoint. If you want, you can access the data. Otherwise, nobody's going to know what is happening in the city. So there's still, like, this framework also requires a lot of support, right? It's not something that is guaranteed to work all the time. Everything requires money. I think that is the core issue. um, I think that is what everything leads to in the end. um I think my last two slides regarding the presentation are just about other opportunities for involvement in Bengaluru and in other places. Is first, there's a hackathon happening this weekend. I can send the link to, it's called Bengaluru Climate Hackathon. If you can Google it, 23rd August, it's happening. So you can take part in it. You can also network with people who are doing work in this space, so that you will it's just more opportunities for collaboration, right? Then you can advocate you can advocate for better data by partnering with the city somehow, or some other communities in the city, to perform Bengaluru's heat watch campaign. I'm sure if the sensor is stuck in the traffic, there will be spikes, which will be very interesting to know, because obviously our city has the world's worst traffic. It is infamous for it. So it would be very interesting to find out what that data looks like. There's also this course called End-to-End Google Earth Engine. I did it last year. I will introduce Google Earth Engine after this. So this is a 3-week intensive certification course, and it was very, very helpful. Um, and the owner of that company, Spatial Thoughts, Ujjwal Gandhi, he is also a resident of Bangalore. So I think there, I am sure if RNSIT wants him to conduct seminars, workshops, he would be more than happy to do so. And then finally, integrating climate into our curriculum, right? As educators and researchers, we could inculcate different projects using all of these publicly available data sets. We need not go out and try to, I mean, building a sensor network is very expensive, right? Each of those sensors that I had shown, which we had deployed in the city, each of them cost at least $250 to $300, which is around 15 to 25,000 rupees, right? And that is just the sensor. Then you need an infrastructure, like you need monitoring stations, all of it becomes a very expensive affair. And but we should start, like, if we can at least do a baseline analysis with the publicly available tools, you can then use that analysis results to ask for funding to build a sensor network in your area, right? All of these are different ways to get the climate action part moving. So yeah, this is to sum up, like, all of the things that we discussed today. We journeyed from the global mandate of SDG 13 down to the street level realities of extreme heat. We've seen why this is critical and how much it impacts health and economy. We've also explored what multi-scale data tools are needed to truly see the problem. And we've also discussed how a collaborative three-legged stool approach powered by, accessible data, vulnerability analysis, and community partnership is the only way to build a truly climate resilient future for all. So, any questions or points that you would want me to talk about? If not, we can go into the demo. Okay, cool then. You can see my browser, right?
Yes.
It should be. Okay, cool. Thank you. So yeah, so let's start with, right? Let me go back here. So satellite data requires us to, so accessing satellite data it has been it had been a very, very big challenge 10 years ago, but I think Google I consider this a gift to humanity when they built the Google Earth Engine platform, which made, satellite data access very, very easy. So let's start with that. What is Google Earth Engine? Right? It is an ability to perform planet scale data analysis on your laptop, on your PC. So Google Earth Engine is a cloud-based platform. Wait, before I go into that, how many of you are aware of this software? If you could, I don't know, raise your hands or, react just to get a sense of this. In the meantime, my email ID is just my last name, first initial. It's there on this slide. I'll put it in the chat too. So yeah, how many of you are aware of this tool and have used it? Nobody? Just wait 5 more seconds. No. Okay. Okay, cool. I mean, okay, Shankar. Okay, that's one person. Nice. Okay, quite a few people. Cool. So for the others, Google Earth Engine is a cloud-based analysis platform. Okay. Um, okay. So QGIS uh, and ArcGIS, those are so let's take a step back from this. These are all what you call GIS tools, right? Geographic information. So that S has different full forms. Some call it science, software, systems, right? Those are the three different uh, areas of geographic, spatial, or geospatial analysis that you can do. If it is geographic information science, that involves you using the data, performing analysis, and then giving out, results or gaining insights from it. GIS, second is what? Software, right? Software and systems, I think both are used interchangeably. Software are the, I think, tools that like ArcGIS and QGIS, which make it easier for you to interact with the the shape files and the maps, and you use them to perform analysis. So Google Earth Engine is one such software tool which gives you access to the satellite data for you to perform analysis on the satellite data. So it's a cloud-based platform. It's like, if I mean, everybody is aware of Google Cloud Platform, right? So this uh, tool, Google Earth Engine, hosts all of the satellite data on the Google Cloud infrastructure and makes it accessible to us researchers and common men using like their cloud infrastructure, right? So you just write one piece of code or you interact with their GUI tool, and then you can access it. But it stores petabytes worth of multiple petabyte worth of data on its massive supercomputer powered cloud infrastructure. So it allows us to ask and answer questions about the Earth's surface at a global scale and over across multiple decades, which was previously impossible without immense computational resources, right? Let's take the Landsat satellite's imagery, which is 30 meters by 30 meters, one pixel. If each pixel has so when a satellite takes pictures of the Earth, it encodes the information in multiple bands. I will explain this in a bit. So one pixel itself could become very, very heavy. So if you have to perform analysis across the entire city, you would definitely run into challenges if you had to do it on your own system, and you would require a supercomputer. So Google Earth Engine enables us to do this in a very friendly GUI coding environment. So the primary purpose of this tool is to empower researchers, policymakers, and developers to detect changes, map trends, and quantify differences on the Earth's surface. All of the computation happens on Google servers. You just send in your script to the cloud. It runs the analysis across thousands of computers in parallel, and it automates that parallelization. So you don't have to manage any of that. You just have to write code about how to interact with the satellite data and pixels. And then it sends back the result to you in the form of a map or a chart or a number, whatever you want. So this is how you can analyze 40 years worth of imagery for an entire country or a city in seconds. So you can run the same analysis for Bengaluru or for Bay Area just by changing your area of interest, right? It's that simple. So, okay. So now what data does this give you access to? That citation is wrong. It should be Gorlick et al. But I'm sorry about that. But so it gives you Landsat. Like I said, it is the longest record of satellite information of our planet. Sentinel, I think it came out sometime in the, I'm just guessing, I think it's early 2000s, and all of the other satellites are late 90s, early 2000s. And it also has data about, terrain, elevation, every surface property that you can think of. All of that data is available on Google Earth Engine. They have 200 data sets, 5 million images. I'm guessing that's this must be at least 10 years old, this image. So it's that scale would have increased massively. Um, and this data set keeps constantly updated because the satellites are still running. They keep sending you the data. Google processes it and stores it on their cloud server and making it accessible to you. So you should think of it not as a piece of software on your computer, but as a massive supercomputer connected to a library of satellite imagery and geospatial data. Next. So this is for the United States, but essentially this is how the satellites uh, capture the data. So this is for Landsat. Landsat is a constellation of, I think, two or three. I think currently there should be three. No, wait, it's two, Landsat 8 and Landsat 9. So both of them go along the Earth, and then they capture each, what do you say, block over here is a tile that they call it. Each tile is a capture of the satellite. And two satellites overlap so that there is no missing data for the entire planet. So this is what happens for the entire planet. So Landsat, like I said, which has, I keep talking about Landsat because Landsat, Modus, Aster, and I think there's one more, EcoStress. So these are three or four main satellites which monitor and observe the land surface temperature. So if you want to do any sort of temperature analysis, these are the satellites that you would go to. But for any other satellites, I mean, any other analysis, you can look at Sentinel, which has a very higher resolution, like 10 meter. Each pixel is 10 meters by 10 meters. So yeah. Uh, so, like I said, as the satellite goes along the planet, it keeps photographing the surface properties of it. It has lots of sensors. So each sensor captures a particular feature of the Earth, and then it gets stacked one on top of each other to create the imagery that you see. And you can interact with every single, I'll show this to you. It'll make more sense when I show it to you. So, yeah, so the problem with satellite data is, let me go back to the image that I had created here. I think it was 19. Stop. Oh God, it was 1990. So you saw a lot of black dots, right? Those are all of the uh, pixels which got masked out because it was too cloudy. So cloud patterns and weather affect the satellite imagery a lot, which is why it which is why you need to couple satellite imagery with ground level observations to get a holistic understanding. uh Sorry. So yeah, let me just skip through these and go directly to the demo. Let Oh yeah, one more thing I forgot to mention is that Google Earth Engine is a completely free software. You don't have to pay for it. If you're using for non-commercial uses, it is completely free. So I should log into a different account. That's why. Let me quickly log in. Not this. Yeah, this login process is a pain sometimes if you have multiple accounts, but I'm sure it will be very seamless for you. It, defaults to my personal account. Now I go back, select this and hit continue. Okay, so this is the interface. You basically write all of your code here. You can search for data sets over here. And this is where I've got a bunch of scripts here, they're all currently loading. Okay, so these are all of the scripts that we have. So let's say I want to search for, I was talking about Landsat so far, right? Let me search Landsat over here. And the latest is Landsat collection 2 tier 1. Not top of the atmosphere. Level 2 dataset. This is what we want. So, uh, so the air quality data is also provided. Yes. So let's check about air quality. I think air quality, I haven't worked with air quality, but there are different satellites for which monitor the pollutants in the air. I will get back to that in just a second. So when a satellite it is collecting the imagery, it collects Google Earth Engine gives you access to like three different levels of that imagery. One is top of the atmosphere, which is above the clouds. One is through the clouds and on the ground. And the other is raw, unprocessed imagery. So what we usually use is, I should not have closed that. This is what I'd use to create that. Let's go back here. What was it? Yeah, collection 2, tier 1, level 2. Landsat collection 2, tier 1. I'll put 9 over here. Yeah. So let's go to the provider website. Sticking to. Okay, that's a dead link. Anyway, so these are the three data sets, and we will want surface reflectance tier 2. Okay. And yeah, so when I was talking about how the satellite captures different surface properties of the planet, this is what I meant. It has 7 bands which uh, capture like ultra blue band 1 monitors like one particular aspect of the surface. Like I think for photosynthesis analysis or something, they'll use band 1 specifically, and then they combine bands 3 and 4 to calculate how much greenery is there the around a given area, all of that. For heat analysis, we are interested with this particular band, STB10. which is the thermal band, surface temperature band. And also you notice that the values are, they are encoded in so Google stores a byte level representation of all of the data per band per for each satellite. This is to optimize their storage. So when you have to use it, you will just have to scroll down and it'll tell you, okay, this, you just copy this piece of code. It'll tell you how to use, how do you scale the bands to get the true value. I'll take that, or you can even, select a CC example here and it'll give you the same, what do you say, data. And then you hit run and there you go. And each of these rectangles that you see are are single tiles. So a city will have multiple tiles based on, so this was the default code is for 2022 month of, what is that, January 1 to January 31st. So this is exclusive. So what we do is, let's say if you want to do it for, if you want to recreate that imagery that I had done for Bangalore, we just, I think I had another piece of code where that's too complex. Not that. How's the geometry of Bangalore? Just give me 1 second. Also, this Google Earth Engine manages the version control for you. So you don't have to make sure to take backup copies of your code or anything. It will all be managed on this platform. Like if you can go to, where is it? Settings. Yeah, you just have to go to clone, git clone. If you do, uh, you'll be able to access all of the code on your browser. I mean, on your local machine, if you do want to do it. And you can share this piece of code with anyone, or give them access to your entire library. You can do any sort of analysis with it. And right now, yes, this is what I'm talking about. Let me take this piece of code. Sorry about that. The main thing which I find very frustrating is there's no debug option. So I just write exit or a random word. And so there's this data set called Gaul, which gives you boundaries at different scales. So this one is Bangalore, but I think it's only the city boundary. So, and each data set is, let me print district. This is the district level boundaries, I think. So it is one big polygon which has all of these coordinates, meaning somebody, you know, drew a polygon, wait, that's drew a shape, something like this. They took points, 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 points. So now that is a random shape, but someone did it properly, but for Bangalore. I'm going to delete this if it's possible. Yes. Okay. So now let us go to Bangalore map.center object. This will help us center the map on Bangalore. Okay, now it's centered here. Now we'll add this administrative layer, add layer. So it gives you code completion also. and I'll hit completion of EE object. So this object we're planning to add to the map is the district visualization parameters. So you can say this is a dictionary. You can say color, I'll write pink. What is the name you want to give to this layer? If you've used QGIS, ArcGIS, it's just you're just adding layers to the map right now. Bengaluru district, and this is shown is this is a boolean, true or false. Do you want it to be shown when you run this code or not? And opacity is like the transparency of it. We don't want to set that. We'll just run that. So there we go. So the shape, the Bangalore district outline, we've got it now. So now when we originally, wait, let me comment this all. So this one gave us that Landsat imagery, right? So now we will extract the Landsat imagery just for the Bangalore district. So this is, we're saying, okay, ee.image collection, earth engine dot, you have all of the docs here if you want to know what to do. So what is an image collection? No, that's not what we want. We want this. Image collection can be constructed by the following. So you have to name the collection, and then you have to, it can either be a list of images or you can just take the entire collection. So when I give Landsat collection 9, so let's go back here, Landsat, let me just select any one of these. So this one, Landsat 8 is available from 2013 to present date, right? And I think Landsat 9 should be from 2021 to present date. So when you give ee.image collection, it will give you all of the images that have ever been collected for Landsat collection 9. So now we will filter it for the past this summer. Let me write it as 04012 2025 05 no 0701, right? And let us stop there, and then we will God print data set. Okay, so now it is fetching. Okay, so you need to be when you're writing this JavaScript code on, I mean, there's also a Python API for this. So if you're familiar and want to work with Python, you can use that too. There are beautiful libraries created for Python too. But in this, what do you say, demo, I'll just go through the JavaScript one because this doesn't involve setting up an environment and everything. So, and this is how you would generally access it. Uh, so you need to be careful with how you're querying the data set. Like it can't show you a list of over 5,000 elements over here. So that's what it's saying. Let us, but it's not more than 5,000. No, did I give the dates wrong? No. Let us add some more. Oh yeah. Oh yeah. It's more than 5,000 because this is global. So it's pulling all of the global imagery, all of the individual tiles that we originally saw across the world. So now let's just filter it to filter bounds to the district that we gave. So now it should give us, there we go, 4 images. So this is what we have, bands. Oh, this is not surface reflectance. We wanted surface reflectance. Which was that thing? Collection 2 T1 L2. This is what we want. And I'll tell you why in just a second. Features, elements, bands. So yeah, these are all the surface reflectance bands. Surface reflectance means what is the light that is reflected from the surface. So each sensor analyzes the light that is reflected from the surface to understand the surface properties. So what we had originally imported was the raw imagery, but we want the processed surface reflectance values. So that is collection 2, tier 1, level 2. So this is what is most commonly used for any Landsat. If you want to go back to 1970s, you'll use collection 5, I mean Landsat 5, collection 2, tier 1, L2, like that. So yeah, so we've got all of these bands, what they had mentioned over here. You've got 8 of these. All of these are flag bands, which nobody generally uses. The main thing is the QA pixel, which we will use to mask out the clouds. And let's go back to this one. So now the sample code again gives us how to. Okay, now let me just run this. Oh, wait, I have to remove this piece of code. Mm, mm, mm. Oh yeah, I have to change the band names because we changed the collection. There we go. So if I just run it, it's going to give me the entire tile which is around the what do you say, the district, the filter bounds. So it will give you the tile which is intersecting with uh, the geometry that you have given. So right now this entire image was captured by this particular satellite at a given time, right? It's not just of the city. So now you want to clip this imagery to your particular district. True color. Okay, no. We want to. Let's move this here. Copy that. Right bands. Here. I don't need that. Where does it say that? Data set. Clip is not. Okay. So what is happening is clip is an image. It works on an image, but data set is an image collection. So when you want a final output, you perform some level of aggregation on the entire image collection. So what people do is they usually take the mean or the median. So let's do median over here. This what this does is for each 30 by 30 meter pixel across, it will stack up the 4 images that we have right now. So when were these 4 images taken? So the last part of the image name, which is 2025 4/6 4/22, April 6th, April 22, May 8, and June 9. So this is, like I said, this satellite has a 16-day revisit time, right? So the images that you get are very sparse. So now it is going to stack up these 4 images, and then for each pixel, it will calculate the median of all of the 4 pixels on all of the 4 images. So that's what we're doing right now. I will remove this piece of code. There we go. This is what Bangalore looks like, and you can see that there is a layer of clouds. So if you have clouds, The problem is that those observations will not be good. Like you're not capturing the true surface properties. So what people do is they mask out the cloud pixels. So for that, you use the QA band, and I'd written a function for it, not this. Yeah, mask clouds. I'll tell you what that is in just a second. Let's go back here. So you take, so this is an image collection, right? So what you do is you map this function, mask clouds, onto each of those images so that one by one, it's like writing a for loop, but you have to use these server level functions that Google gives you, so that you can't use looping constraints here. You have to use map and I think it's like Apache, uh, what was the tool?
Apache Hadoop.
Hadoop, exactly. Yeah, yeah. Sorry, that one. You have to use mapping functions. There are no looping constraints. So this is the main challenge. I think you have to get used to thinking about your code in a different way. How can you perform uh, operations on a single image, and then you map the entire image collection to that function so that the operation happens across the entire collection. So we are mapping it. So for each image, we are taking the QA pixel. What is the QA pixel? It gives you like the cloud level properties. Where is the documentation image properties? So there are two ways of removing cloud pixels. This is what I use. And wait, where so it's a bit of, I think, seven. I mean, it's a digit with 7 bits, 8 bits. Yeah, right. So you have to set each of these bits a one value, um, because the first bit signal. Where is the documentation? It's supposed to be. It's hard to visualize this. Okay, that website is down. Okay, it's here. Where's that documentation? Not that. I'm sorry. I will get you that documentation later. But each bit here represents a type of cloud. So one is a fill, means that pixel is entirely covered in a cloud. The second bit from the left it means it's a cirrus type of cloud. One means it's a snow. So you are collecting all of the pixels which have any type of value for each of these pixels, and then you are filtering out those pixels. You're just masking them, you're just setting them all to 0, so that you are not taking data from any of those cloudy pixels. And once you average out the stack of the images, those clouds will go away. Let's look at that. There you go. You might notice some holes here and there. Let's see if you can see a pink in the background. That means those pixels those pixels were cloudy across all 4 images. Okay, this is how it's generally done. You mask out the clouds, and let's go to the inspector layer, and then we can inspect one of these layers. And let's see what it shows us. So for each band, it is giving us a very large number. And for STB10, which is a thermal band, it's a some random number. Why is that? Because we haven't um, scaled our the band values, because Google stores it in byte representations, so we have to bring back the original values. For that, we apply scaling. Let me copy that. This again is a this is also available in their base example code, so you don't have to remember any of this. You just map out the scaling, apply scaling. So now the color has become black because the range which we had given for pixel values was 0 to 30,000. That obviously has to change now. So here we can go. This is RGB. So band number 4 is red, 3 is green, and 2 is blue. I think you should also be able to see that over here. 4 is red, green, and blue. So that's how we were able to get the true color representation of it. And this stretches the range to like the 98th percentile, and that gives us a very high resolution 30 meter by 30 meter data for the entire city of Bangalore. And here let's see, I touched a random pixel. Let's see. Okay, let me touch one of these pixels. It looks like a built up area or a ground that has a temperature. ST beta is still not scaled. Thermal band is not scaled. Should be. When I had created that across the years GIF video, I had to combine multiple satellites. So I think there's some residual code left. There should be thermal band. See, it should ideally be, what is it? In Celsius. STB10, it's still not scaled. Why? Let's go here, see example. Okay, and then we'll just copy this value. Their example into ours. Scale factors. What is the 310? Okay, that's in Kelvin. So now we will just subtract 273 point. Oh, what is it? 273.1. This is such a 273.15. So, okay, there we go. This should give us the values in Celsius. STB10, okay, 32 degrees. Okay, finally we have our imagery in the correct representation. Let us go back to the correct view. Let's switch the base map to satellite and close this. I'll turn off this so that we don't see the pink layer at the bottom. Remove that. So, okay. Okay. This will give us, so you can toggle the layers. So let's go to some very urban area. Okay, wait there, that field. And if you increase the brightness, you can see that each pixel is a 30 by 30 meter grid. So right now we are looking at the true color representation of the image. We can also just look at the surface temperature. So for that, you will say bands. I want to visualize just the surface temperature band B10, and you can use different colors. You don't have to depend on, there's a different library of color palettes. What was it? Palettes. There we go. There are a lot of community libraries where you can use their created palettes. So any of these palettes to visualize temperature. I'm just going to use that and then say palette use palettes dot matplot lib dot inferno, and then how many colors? Let's say 7, and this will be your LSD band. So once you run that, it will give you ideally 3 layers now, because we are also mapping the Bengaluru district layer. There we go, it's loading. Okay, so now you have to scale the bands. Like, you can do this automatically. You can programmatically calculate the 98th percentile and then give the min and the max. It will do it for you. Like, let me turn that off. So there's your true color is appropriately scaled. Now let's scale the surface temperature. Here you can see that the Inferno color palette is chosen, and let's give the 98 percentile. So you can see that across the city, the range of temperatures is in between 29 degrees Celsius to 43 degrees Celsius. I'll hit apply, and we can see this is just the land surface temperature. And this map is a representation of the city Bangalore. Uh, this is the summer representation, summer of 2025, right? I don't think there was any image from July. Oh, we didn't take July. Yeah. So this one is a composite image of the land surface temperature of Bengaluru in 2025. So this should give you a basic idea of how to work with it. And once you know these are like these basics, you can then, do some advanced stuff like, let's go back here. So this is just the same code that I had written, but I combined Landsat 5, 7, and 8, like 7, 5, 7, 8, and 9, because let's see, Landsat 5 had the historical data and said this one. This has from 1984 to 2011. So that's why you'll have to stack up multiple satellite imageries to create some visualizations like this. So here I'm just asking it to give me a video URL, and you can just copy, you can go to that URL, and okay, I'll have to rerun this code. It'll give me a URL. You could also, wait, we just created this imagery, right? You can even export it to your drive. Export dot, if you hit and then control enter, you'll get image dot. You can export it to your Google Drive account. It has all of these values that you need to fill in. Let me, okay. So dictionary, right? So let's fill them in one by one. What is our image? It is the data set dot, which is clipped to the the district of Bangalore. And then description is for, so whenever you have to export a data set out of Google Earth Engine, you have to create a task. It's basically like submitting a job to the server, and then you wait for the server to finish the analysis, and then it'll give it back to you. So now you're writing the name for the job. So this will be export LSD Bengaluru 2025 summer. And this is the drive folder that you want to save it in. If you give it a blank value, I think it will save it in the root. And next is file name prefix. So this is the file name. I'll give it 2025 summer LSD. Dimensions, you don't have to bother. It will automatically set for you. Region. If you had not mentioned clip over there, you can mention district over here so that it will clip it for you. Scale is, okay, scale is something very important that you need to keep in mind of. What do you say? Landsat imagery is at 30-meter resolution, right? But if you want the output imagery to be at, let's say, 100 meters, you can give it a different scale, and then Google will automatically aggregate it up for you so that your output imagery can be at whichever scale you want. So if the base imagery is at 30 meters, you can aggregate it up to 100. But if it is at 30 meters, you can't go down. Like, that is the limit. So scale, you can just leave it or you can give 30. CRS is the coordinate reference system that defines how the image will look when you plot it on a map, right? I don't know what the CRS for Bangalore is, so I'll just leave that. I'll let Google handle it for me. Max pixels, again, if you're doing city-wide analysis or country-wide or global-wide, you can set the max pixel so that the job doesn't terminate. And you don't have to bother about shard size, file dimensions, skip empty tiles. It's all default. File format, you can give that it's a geotiff, but this is also not needed. Format options, priority, you don't have to do any of that. And that's that. Did I miss something? It's a mismatch. Oh, this, there we go. So if I run that, it should show up in my tasks. So these are some of the past tasks that I had run. Okay, so it has showed up here. I can just say run. It'll ask me the same details again. You can just choose to change it here if you want to. Saving it to drive, this is the file name, whatever. And then you hit run, and then it will run in the background. It shouldn't take long because it's just one image. It should take less than a minute to run. In the meantime, I can show you some of the other stuff. So here we had done the same thing what we did for one image across one summer. Here I just stacked up multiple years data sets across multiple satellites. I can give you the code later. Next is so you can also interact with some climate model data. This is the ERAS 5 climate model data. So just know that climate models have very, very coarse resolution. You'll know what I mean in just a second. Stretch this to the actual range, apply. Okay, so you see each pixel is, I think, at least 30 kilometers wide. So it's very, very low resolution. So climate model data is only useful if you're doing a larger area analysis. So I'm just saying that this is also another data set that you have access to. Next is, where was it? Was it this one? Okay, we're running out of time, so let me just show you some of the other stuff that you can do. So here, this is an interactive map where I have selected, you can select different data sets to be visible and then you can slide through it. The data set on the right is about impervious surfaces which have come up over the years. So the lighter blue color means they have been there since the 1990s, and red color means that's a building or road or something that has come up recently. And then you can overlay it with your temperature data to sort of make it explainable. I just used it to make some of the visualizations that I had um, shown in the presentation. But yeah, this is an interactive app. You can uh, convert this into so if you write get link shareable snapshots, you can make this shareable in the same state, or you can convert it into an app, right? So you can use this in different ways. There's one last thing that I wanted to show. Simple land cover classification. We're running out of time. I will do this very quickly. So this is a simple, very simple random forest classification algorithm that I had run, created it last night. So each of these pixels, so as you can see, uh, I defined four different, I can define one more for an example right now. This, I'll create this as what was missing. I'll say roads, okay? I'll give it, you have to import it as a feature, because if a feature you can, like for random forest, you need classes, right? So you can give, this is the property over which you are performing the classification on. So there are four existing already. I'll give this as a new class, and then I'll give it a color, let's say black. Okay, and then that's the color. So now we need some training data for roads. So roads, obviously you're not supposed to use Landsat for it, right? Because this road, obviously it is smaller than 10-30 meter scale, which Landsat cannot see. I'll just put some random training points and then see what Landsat gives us. Dairy Circle, right? Hosur Road. So roads has 5 data points as training, and the others have, I think, 7 to 10. So the same thing you'll do, you'll take the imagery, you'll scale it. So if I took the same summer imagery, and then training data is trees, barren land, water, buildings. Now I'll add roads also. You'll define this as the collection of training. And then what you do is wherever you have the points that you have dropped, it will take each of those pixels as a training pixel. And then you are building a simple random forest classifier based on that. So if you run it, this should change to 5, and then this will add 1, 2, 3, 4, 5, 6. Done. So now you'll see some blacks also. Obviously, this is not going to be accurate. There's a lot of, let's see what it has. I mean, it could, let's switch to satellite, make this transparent. I mean, it's not bad, but like I said, since the resolution of Landsat is 30 meters, it has identified that this is a road, but it assigned that entire pixel as the road. So that's why it's a little coarse. But yeah, it's not bad. So this is an overview of how you could use Google Earth Engine for different sort of land cover change analysis. There's one, oh God, thermal. Just give me 1 second. There's one last thing I wanted to show you. Okay, this is the one. So I took the temperature data from, when was it? 2015 to 2024. Okay. And you can even plot charts and graphs based on that. So you can see how land surface temperature changes. And interesting thing is Landsat satellite has a revisit time of 16 days, right? So that's why it is very coarse. But since MODIS has you have data for every day, this one is a little more, smoothed out. But yeah, I think I can share code for any of this. The only thing I would encourage is uh, end-to-end end-to-end Earth Engine. This is the course that I had taken. It's by Spatial Thoughts Open Courseware. So they also provide workshops. I mean, I think you can sign up for this. And then the other thing is Python GE. It's called GE Map. This is a wonderful what do you say, library which you can use to they've also got companion videos, so you can use this library to learn how to run Google Earth Engine locally. Okay, that's it.
Thank you, Rahul, for your wonderful session. Dear audience, any doubts? Any queries? Okay. So let me conclude with the session. Your presentation highlighted the alarming trends of a climate change, bringing to light its human cost and the urban amplifier effect. We are very truly grateful to you for connecting the dots between the global goals and the local solutions and powerfully reminding us why immediate climate action is needed now. Your explanation of SDG 13, along with the roadmap, emphasizes the data, environmental sensing, and community partnership, offered us valuable insights into strengthening resilience and fostering the greater awareness. The way you demonstrated and visualized the use of a long-term satellite data, that is the satellite 8 and satellite 9 data, by using a Google Earth Engine software to identify the hotspot insights from the global network of weather stations and the deployment of dense urban sensor network, was both informative and inspiring. On behalf of all the participants, I extend our heartfelt thanks to you for sharing your expertise on big data analytics for climate insights. Your session has truly motivated us to contribute actively towards a sustainable climate solutions. Thank you, Rahul. Thank you all the participants for joining the session. Thank you all.
Thank you.
I've shared the feedback link in the chat box. You can fill the feedback link. Thank you.